Imagine you want to query an external database. And how this is typically done is use a dedicated query language, in this example it's SQL, to perform that query. And as with any programming language, this query language has a syntax. This is what different words are and how you form sentences from words. And it also has semantics. And the semantics is what this sentence means to the computer. However, if you have a really complex application, you don't write your whole application in this query language. That wouldn't be possible. So what you typically do is you combine this query language with a general purpose host language. Now, this combination, however, is tricky because the query language has a different syntax than the general purpose language. And it also has different semantics than the general purpose language. And what is more, it has probably no tools or different tools than the general purpose host language. And to solve this problem of combining different languages together, people have been coming up with various approaches in the past. One very straightforward approach is just to call the external language from your main language, from your host language, like that. So you have, for example, a string that you pass to the other language, and this query language will then return the result. And this is what is called an external language. And it has various advantages, but also a lot of disadvantages. The advantage, of course, is that this external language can basically do anything it wants with the syntax and semantics. However, it's often expensive to have an external language. First of all, it's difficult to implement a new language from scratch. And second, it often has no tool support because it's already expensive to implement the language. And it's also error-prone, this communication between your main language, host language, and the external language. And that's why people thought about a different approach. And what they do here is they use a so-called internal language. An internal language is essentially a subset of the host language. It makes creative use of the facilities of this host language and tries to model, in this example, a query using a subset of the host language. And while such an internal language works very well with the existing tools of the host language, it has the problem that it's really a subset. So it's kind of restricted, it's very limited, and in general it might be very difficult to express the problem. So for example, somebody that is used to the SQL query language might not be able to immediately write such code. Now, what would be obviously the best if we could embed this external query language right into our host language and use it from within there. So in this example, we have the host language around it, and then the query is directly embedded into the host language. So it combines the two approaches of the external and the internal language and basically takes the best of both approaches. However, the problem here is that only very few systems support such a tight embedding into a host language. So existing approaches, either they build a new host language, which gives the problem of compatibility with existing code. So if you have existing code, it might not work in such a new language environment. Or, and this is, I think, even worse, they break existing tools because they do some kind of code transformations beforehand, and that breaks existing tools of the host language. And this is why we propose a new approach, and we call this new approach Helvetia. And we take that from, so Helvetia is the Latin name of Switzerland, and we take the map of Switzerland as a metaphor for it. So with Helvetia, we want to build on a conventional language. We don't want to invent our new language, but we want to reuse and facilitate the existing language and its existing tools. Furthermore, with a new approach, similar as in Switzerland, we want to support multiple context-specific languages. So depending on the location in the code, we want to support different embedded languages. Furthermore, as you see in Switzerland, people and goods can arbitrarily travel around between different languages. In a new approach, we want to have homogeneous code and data abstraction, which means that the execution flow of the program can arbitrarily swap between different languages and results can be passed around to different languages without an expensive conversation. And last but not least, as we have in Switzerland, we have a uniform law system, we have uniform supermarket chains, we have uniform money system. In the Helvetia system, we want homogeneous tool support. That means the same tools can be reused by different languages, and developers don't need to actually learn new tools or to build new tools. So, this leads me to my thesis statement that I'm going to read for you. So, to support the seamless integration of context-dependent languages without breaking the tools, we need, first, a language grammar that can be changed by language extensions. Second, a first-class language description used by the development environment. And third, a transformation mechanism of the embedded language into a common executable representation. This slide depicts the architecture of the Helvetia system that we are going to propose, but it's also at the same time serving as an agenda for the remainder of this presentation. At the lowest level is the host language. We are not going to talk about this any further. We consider the host language as given. We don't want to change it. Right? Then the central part of the Helvetia system is the lowest layer, the Helvetia core system. It provides a rule engine to intercept the compilation and the tools. It is essentially the provider for the high-level language box model that is implemented on top of the Helvetia core system and that provides fine-grained and modular language changes or extensions. Then the driving force between the Helvetia system and the language boxes are dynamic grammars that I'm going to talk about in the third part. And throughout the presentation, I will already show you a few examples of language extensions and language embedding that we can do with this system, but I would like to wrap up this presentation with three more particularly interesting examples, I think. So to start out, let's dive into the Helvetia core system. So when we started with Helvetia, we wondered about what types of embedded languages are there and what types of languages do we want to support. And we kind of looked at a delta approach. So we wanted to see how the embedded languages differ from the host language they are going to be embedded in. And syntax, vocabulary, and semantics are essentially the three things that can change between different languages. And we wrote down all the combination and we looked at the combination that we want to support. So the first combination is obviously trivial. We don't change anything. So host language embedded into host language, that works anywhere just like that. That's not interesting. Another not so interesting combination is when we just change the vocabulary. Now that's just an internal language and it doesn't require any more thought. So it's also not an interesting combination. More interesting combination, however, is when we change the vocabulary and the semantics, and we take here the term from natural languages. A pidgin is a simplified form of a language used for communication between people not sharing the same language. And it's basically a simple form of an embedded language because we don't have to write a new parser to support it. We just have to define a new vocabulary, which is typically very easy, and we have to do some semantic transformation to give it a meaning to this new language. Then another kind of language that we want to support are creoles. Again, we use a term from natural language. So a creole is a mother tongue or full language formed from the contact of other languages. It's basically the most general type of languages that we want to support. We can change the syntax, we can change the vocabulary, and we can change the semantics. So we can do whatever we want. We can embed any language we want with a creole. Then the third type of language that we want to support are Argo languages. They are kind of special, and some people have accused that this is not really a new kind of language. What it does in Argo is it just changes the semantics. And how that is useful, I will show you in an example at the very end of this presentation. Now there are three more combinations that are possible of changing syntax, vocabulary, and semantics. But if you have a look closely at these combinations, you see that they don't really make sense. I cannot define a language without also specifying some semantics or at least some vocabulary to it. So what we are going to look at, or what we are going to support in Helvetia, are basically these types of embedded languages. And how we are going to do that, I'm going to show you in the next few slides. So that's a basic compilation toolchain as you see it basically in any programming language. So a compiler takes the source code at the beginning, it parses this source code, it does a syntactic analysis, it does symbol resolution, which is the semantic analysis, and it finally generates some code, some machine code or bytecode in the code generation step. And so what Helvetia does here, it adds into the existing compiler pipeline some extension points that can then be accessed or changed by a rule system. Now what you see here is what is typically called an extensible compiler. A compiler that can be changed and adapted on the fly. But we take this model a step further to also use the same rules to adapt the tools and to make the tools changeable with the language. So for example, we support custom syntax highlighting, custom error reporting. We can even support custom refactorings for a specific language. We can support auto-completion, code folding, contextual actions, basically anything that you expect from a dedicated IDE. And then depending on which rules are active, we can also support the different types of embedded languages. But before I go into details here, I would like to show you some quick examples. So that's a shape from a visualization framework called modular. And to build this kind of shapes, the modular team used to write code like that. And it's quite complicated code for getting a simple shape like that. And now I'm going to show you how to build a pidgin language. And that's an example of the same code as a pidgin language. So it's still valid host language code, but it syntactically has no meaning. So we have to define a transformation to the host language to make this code again meaningful for the compiler for the machine. Similarly, and this is where the compilation then goes through. So we reuse the host language parser, we perform a custom transformation, and we generate executable code similar as the standard pipeline does. We can take this a step further, right? Because the pidgin language might not be what the developer wants, but maybe the developer is a graphic designer and more used to CSS. So he would like to have something that looks more like CSS and that he is more accustomed with. So we can do that, and we can even reuse some parts of the host language, as you see here in the example of the block closure, of the lambda closure. And here we provide a custom parser, a transformation, and it goes into the same executable code. So we have different ways of going through this compiler pipeline with the Helvetia system. So just to quickly summarize the Helvetia system, we support a conventional language because we build into the existing compiler toolchain. We have context-specific languages because the rules can activate or deactivate themselves depending on the context they are used in. We have homogeneous code and data because everything is in the end transformed down to the same executable code model, to the same executable, same execution engine. And we also have homogeneous tool support because we are able to access the tools with the same rule system. And of course we are able to support Fiction, Creole, and Argo languages by just enabling different paths through this compilation toolchain. So that's a quick overview of the Helvetia system. It's an extensible compiler that also affects tools, and it provides the necessary hooks for the language boxes implementation. So if we step back and look again at this map, you see that there are quite a few areas here in the map where languages are really tightly interconnected. They are just not that clearly separated anymore. And this is something that the Helvetia system by itself doesn't nicely support. The Helvetia system works really well if there is one language active at once. But as soon as there is a second language active, the different rules obviously start to conflict with each other. And this is where the language boxes model comes to the rescue. So let's again have a look at the example of this query language and how we can embed that into a host language. So that means we want to really pass this new language or use this new language into a completely different, into a different host language. And the language box model is rather simple. It looks like this. A language box consists of a language scope, a language concern, and a language change. And I'm going to quickly go through these three things and explain how that exactly works. So the language scope is the most simple thing. It basically answers the question, when is a language box active, or where is a language box active? And that can be defined from two sides, either from the user, so the user can import or add a language box to his code, or it can be also defined from the language box itself, so a language box can say, okay, I'm enabled in the complete system, or just in some packages, some classes, or some methods. That can be useful if you have a framework that uses the dedicated language to express something and is commonly used in this case. So that's the language scope. Where is the language box active? Then there is also the language concern, which essentially defines the semantics of the language change. And this is mostly a transformation of the embedded language into the executable host language. And similarly, and you will recognize these items from the Helvetia system, we can define also the semantics for the tools using the language box infrastructure. So we can define highlighting, custom contextual menus, custom inspectors, custom navigation facilities, search, various code editing concerns, refactorings, code completion, etc. to affect the embedded language, or to affect the tools and how the tools work with the embedded language. The last part of the language box is probably the most interesting thing, and this is the language change. It defines the syntax of the embedded language. And just to quickly show you how that works, is the language box language as well. And then we end up with a custom host language. And then this custom host language is used by the compiler and all the tools in the system. And we can end up with a situation like that. So in this example, you have as host language Smalltalk. Then you have embedded into the host language Smalltalk SQL query. Inside the SQL query, as a host language, you have embedded again Smalltalk. And inside Smalltalk, you have embedded regular expressions, something that is not supported by default in this host language. So we can have a tight interconnection of different languages with the language box model. So that sums up the model of language boxes. Language boxes provide a fine-grained model for modular language changes, and with the various concerns, we can access the parts of Helvetia and how the tools are affected in the development environment. So the next interesting thing are dynamic grammars. And dynamic grammars come essentially into play here in the language change. So if you remember, the language change is essentially a delta to the host language. Or more precisely, it's a delta to the host language grammar, because it is the grammar that describes how the language looks like. And what we do here, or what we do in the language change, is essentially a grammar transformation. Now, how can we do grammar transformations? With traditional approaches of representing grammars, unfortunately, transformation or compositions do not really work well. So that's a typical way of specifying a grammar for programming language. Here, the complete grammar is written down or generated as host language code. And obviously, or for obvious reason, we cannot easily transform or regenerate that code, because that would be expensive to do it from scratch for every single context where we want to compile code. Another common approach of describing grammars is using tables. And as you see, that doesn't look like it's easy to work with, or that it's easy to compose or easy to transform. Basically, you always have to restart from a more tangible model and regenerate these tables, which can be difficult in practice or time-consuming. So what we use here as a solution is a combination of various alternative parsing and grammar technologies. So first of all, we use scannerless parsers. That means there is just one entity. We don't split the parsing into the scanning and the parsing part. And that makes combination much easier, because there are no two independent entities that have to be merged together. So we just have one. And then we also use parser combinators. Parser combinators model parsers or grammars as a graph of objects that are modular and that then can be composed and changed on the fly. And to quickly show you how that looks like in practice, I have written down here a simple example of a grammar from the SQL grammar, by the way, that parses identifiers. And this is typically visualized in a flow graph like that, but with parser combinators, we model that as a tree or as a graph of object. It's actually a graph, right? So it's a sequence of a letter and many or 0 or more choices of letters or digits. And now we have a graph of objects or function objects, and now we can of course easily apply grammar transformations to that graph of objects. And again, I've made a simple example. So if we wanted to change the identifier to also support the underscore character as a valid identifying character, we can apply this transformation, and we end up with a graph like that, right? And similarly, because this is really something very dynamic that you can change all the time, we can also apply optimizations to that. I'm not going into that topic in this presentation, but this is very useful when there are a lot of automatic transformations to normalize and make the grammar efficient again in the end of the compositional transformation. So in this example, we could reuse the common things and we could flatten out choices, for example. Now, this was in general about grammar transformation. But what we actually want to do with language boxes is grammar composition. So we want to compose different language extensions with each other and with the host language. And a language change essentially always looks like that. So it says insert a new grammar fragment before or after a grammar production of the host language as an additional choice or as an additional sequence element or even as a replacement into the language where the grammar should be embedded in. And in the example of SQL, this simply reads as insert the SQL grammar after the expression production of the host language as an additional choice. And visualize, this looks like this. So if we assume that the expression production in the host language looks like that, so it's either a variable, a literal, or a parent expression, we just add the SQL grammar as an additional choice. So these boxes here look actually quite simple, but in fact these are full graphs of complex grammars, right? In this case, it's a full-blown language that is just passed in there as an additional choice. Now, the most interesting thing, of course, is how do we deal with conflicts and ambiguities in this case. So, if I ask you what kind of language that is, obviously everybody would say that's clearly SQL. However, depending on the context it is used in, it's not that clear anymore. So, in fact, in this case, where the host language is Smalltalk, this could be well enough also be a valid Smalltalk expression. And now this is a problem. So with traditional approaches to grammar composition, that would lead to an immediate error. It would say this is a shift-to-use conflict or something, and it wouldn't allow you to compose these two languages with each other. And we would need to somehow disambiguate these languages by adding a special token to it that would say, yeah, now this is clearly an SQL expression that comes. However, this is not really a general solution. Imagine we want to reuse this SQL expression in a different host language or in a different embedded language. And there maybe the situation is completely different, so we would need to add a different token. So it's not really a good solution. So our solution to this problem is that we use parsing expression grammars, or an idea from parsing expression grammars. And in parsing expression grammars, they order choices or prioritize choices. So whatever comes first gets the priority of whatever comes next. So if you write it like that, so the host language expression comes first over the SQL expression, and we basically get rid of the conflict like that. Because yeah, whatever comes first can eat the input. Now, however, this might still surprise the user, right? It might surprise the user that an expression that he typed is a host language expression and not an SQL expression. So the developer of the language extension might be tempted to turn that around and say, okay, the embedded language should take precedence. So there is always this choice that the developer then has to take. And I think that's not really a good thing, because depending on the context, the user might want to choose something else. So what we did, or what idea we have here, is to introduce or reintroduce the unordered choice into the parsing expression grammars. And in fact, it's quite simple to implement such an unordered choice in parsing expression grammars. Said in English, it simply tries both languages and only accepts the language if exactly one succeeds. So that removes the ambiguity. In case of an ambiguous expression, we essentially end up with an error. Or we can even extend this allowed choice with a UI interaction. So we can pop up a dialog and ask the developer what language extension did you actually meant. In this particular context, your language extension is ambiguous and it's not clear if this is the host language or the SQL language extension that you type. And then the user can select that, and the parsing can continue on the fly with the right choice. The system can remember this choice for the particular context, so it won't ask the developer again, and it will be remembered from then on for this particular case. So these are dynamic grammars that can be dynamically changed, recomposed, and that avoid conflicts and can nicely handle ambiguities. So to end my presentation with, I would like to show you a few language and tooling extensions that we wrote as a validation on top of the Helvetia system. And you can find a full list of examples at this URL here. We already looked quickly at two examples. First of all, the modular visualization example, and second, the SQL query language example. And now I would like to quickly show you three more examples: transaction memory, quasi-quoting, and program checking. So the first one is transactional memory. Transactional memory is an interesting language extension because it's not naturally seen as a language extension. Most people that have been working with transactional memory try to implement that on a hardware level, or at least on the level of execution engine. But what we do here with this language extension is we implement it in Helvetia, and we use an Argo language for that. That means it just changes the semantics of the language in the system. So we basically rewrite all the state access to go to a transactional context, and like this we can roll back, for example, changes to when changes are made to an object. So with this example, we were able to implement transactional memory in a conventional host language without changing any of the runtime infrastructure and without breaking any of the tools. So in the debugger, when you step through transactional code, it continues to work. And it even continues to work with external libraries that might not be aware of the transactional semantics that have been added to your development environment. Then another interesting language extension that we did and that we used quite heavily in the implementation of the Helvetia system itself is quasi-quoting. So those people that know Scheme or Lisp are certainly familiar with these kind of quoting expressions. It's obviously a Creole language that has been implemented using the Helvetia system, and it's extensively used in the Helvetia system itself to specify the transformations between the embedded language and the host language. Third example that I would like to show is domain-specific program checking. That's, again, quite a special example because it doesn't actually change the language, it just reuses the Helvetia infrastructure in a different context. And what it uses it for is for program checking of internal domain-specific languages. This is something that was not supported by the tools. Up to then, it was not possible to tightly scope different internal domain-specific languages and the functionality or the tests or the program checking tests on them. and with Helvetia we were able to implement that quite nicely, and this is also heavily used in industry to check the C-side and Margaret code. So this was a quick overview of a few language extensions that we implemented as a validation of the Helvetia approach. So to end up my presentation, I would like to quickly go back to my thesis statement. So we set out to support a seamless integration of context-dependent languages without breaking the tools. And we did so basically by providing three unique parts. So first of all, a host language grammar that can be changed by language extensions. These are the dynamic grammars that can be recomposed and transformed on the fly by the language boxes that provide a first-class model of modular language changes that can be independently composed and imported into program code. And last but not least, we provided the Helvetia core system, which is the provider of the necessary hooks for the language box implementation into the compiler toolchain and into the tools of the host programming environment. So thank you for your attention. Now I'm open for questions.